everyone. Let's begin our discussion over the questions on mathematical induction. First question is, for n belonging to the set of natural numbers 10 to the power n minus 2 is greater than 81n if. So now the options are n is greater than 5, greater than equal to 5, less than 5, greater than 6. Here if you try to begin with n equals 1, because that is where natural numbers begin from, for n equals 1, you're going to see 10 to the power 1 minus 2, that is minus 1, is greater than 81 into 1. That means 1 upon 10 is greater than 81. This is clearly false, right? This is clearly false. This is minus 2 actually. This is 1 minus 2 gives you minus 1. Here if you see 1 upon 10 is greater than 81, that means 0.1 is greater than 81. This is completely false. So for n equals 1, this statement is not true. For n equals 2, if you see, for n equals 2, it is 10 to the power 2 minus 2, that is 10 to the power 0, which is 1, is greater than 81 into 2. This is obviously false. Again. So for n equals 2 also this statement is incorrect, it is false. For n equals 3, you have 10 to the power 3 minus 2, which is 10 to the power 1, is greater than 81 into 3. This is again clearly false, right? For n equals 4, let's see, 10 to the power 4 minus 2, that is 2, is greater than 81 into 4. That is 100 is greater than 81 into 4, again false, right? This is nothing but 324 and 100 is not greater than 324. For n equals 5, you have 10 to the power 5 minus 2, that is 3, is greater than 81 into 5, which is what? 1000 is greater than 405. Yes, this is true, right? Similarly, for n equals 6, you will see that 10 to the power 6 minus 2, that is 4, is greater than 81 into 6. Yes, this is also true. This is again true. And that is what is going to continue. So you are seeing that from 5 onwards, this statement is coming out to be true. Before 5, it's not true. 5 onwards, it's true. So this is holding if n is greater than equal to 5. Clear? Next question says that for each n in n, the correct statement is what? Now here, whenever the question is talking about for each n in n, begin with n equals 1 for sure. For n equals 1, let's see which statements are correct. Fine. If I talk about the first statement, for n equals 1, 2 to the power 1 is less than 1. That is 2 is less than 1. Very clearly it's false. So forget about it being true for every n in n if it is not even true for n equals 1. Talking about the next statement, n square. So 1 square is greater than 2 to the power 1. That is 1 is greater than 2. This is again false. Clearly, this is not that statement which is true for every n in n. Then it is C, n to the power 4 is less than 10 to the power n. For n equals 1, I am checking. Yes, 1 is less than 10. This is true. If I talk about the next statement D, it is 2 to the power 3n. So 2 to the power 3 into 1 is 3 is greater than 7 into 1 plus 1. 8 is greater than 8, again it is false. So clearly this is also not true. This was true for n equals 1, but for n equals 1, none of the other is true. That means this is only true for all n in the set of natural numbers. Clear? Next you have the statement given involving n to be this, then Pn is true for what all values of n. Let us write Pn. It is 4 to the power n upon n plus 1 less than 2n factorial whole upon n factorial whole square. For what values of n it is true? If you talk about n equals 1, this becomes 4 upon 2 is less than 2 into 1 is 2, 2 factorial is 2, upon 1 factorial is 1. So you get 2 is less than 2, which is again false. So for n equals 1, it's not true. If I talk about n equals 2, for n equals 2, it becomes 4 square upon 3 less than, this is 4 factorial upon, this becomes 2 factorial, which is 2. So you get 4 square, which is 16, divided by 2 plus 1 is 3, is less than 4 factorial is 24 divided by 2. Right? This is 2 factorial whole square. So this is 4. Okay? You can clearly see this is not true. This is not true. Here if I try to analyze the situation, this is true for what all values of n. Now the moment this has started, just understand this very carefully. Clearly for n less than 0 it can never be true because n comes from the set of natural numbers. So n less than 0 is definitely false. It is not true for n equals 1, right? If it is not true for n equals 1, this option is also eradicated because this option says that for n equals 1 and greater than 1 this is true. But for n equals 1 it's not true. Similarly, for n greater than 0 also this is eradicated. Why? Because n greater than 0 involves n equals 1, but for n equals 1 this is not true. So this is also wrong, and therefore there was absolutely no need for us to talk about n equals 2 here as well. Only till here your argument would have been sorted and you would have said that the answer is option number D because first 3 are logically incorrect. Clear? The very fact that it is not true for n equals 1 has helped me to eradicate these 3 options, and this has become the correct one. Okay? Moving to the next one, it says that by the principle of mathematical induction, for all n in n, this expression comes out to be equal to what? Now this expression will be equal to this or this or this or this. I will have to decide by putting values of n. If I put n equals 1, just see, if I put n equals 1, this is my left hand side expression. So you get 1 upon 1 into 2 into 3, that is it. Right? You get 1 upon 1 into 2 into 3, that is it. If you put n equals 1, what do you get? 1 upon 1 into 2 into 3. So left hand side becomes 1 upon 1 into 2 into 3, which is 1 upon 6. Now right hand side, let's see which among these right hand sides give me 1 upon 6 for n equals 1. If I put n equals 1 over here in A, if A is my right hand side, I get 1 into 2, that is 2, upon 4 into 3 into 4. This is not equal to 1 by 6. If my RHS is B, then you get 1 into 4 upon 4 into 2 into 3. This 4 cancels, you are getting 1 by 6. If I put C, then I am getting n into n plus 2. That means 1 into 1 plus 2, that is 3 upon 4 into 2 into 4 into 2 into 4. This is again not equal to 1 by 6. 3 plus 1 is 4, 1 plus 1 is 2. This is not equal to 1 by 6, and therefore RHS cannot be A, RHS cannot be C, RHS has to be equal to B. Right? So this is how you can check. You don't need to actually carry out the entire induction process to find out what it is equal to. For different values of n, you can get sorted out answers that can help you to chuck out the other options and hence take the right one. Next question says what? Let's see, the product of 3 consecutive natural numbers is divisible by what? Now here we need to form the statement which is involving n. So P of n will be product of 3 consecutive natural numbers, n into n plus 1 into n plus 2. That is going to be my representation for product of 3 consecutive natural numbers. If I put n equals 1, now this is divisible by what? If you put n equals 1, you get 1 into 2 into 3, which is 6. If you put n equals 2, you get 2 into 3 into 4, which is 24, which can be written as 6 into 4. If you put n equals 3, you get 3 into 4 into 5, which is 60. So you are getting that each number which is obtained by plugging in different natural numbers in place of n is actually coming out to be divisible by 6. If it's true for 3, it's going to be true ahead as well, and therefore 6 is going to be the answer of the number by which the product of 3 consecutive natural numbers is divisible. Okay? Moving to the next question, we have this inequality is true for what all values of n? Let's try for n equals 1 first. If I put n equals 1, you get 1 factorial, which is 1, is greater than 2 to the power 1 minus 1, which is 2 to the power 0, which is 1, and this is false. Right? For n equals 2, this becomes 2 factorial is greater than 2 to the power 2 minus 1. Right? 2 factorial, which is 2, is greater than 2 to the power 2 minus 1, which is 1, and therefore this is again false. If I put n equals 3, I get 3 factorial, which is 6, is greater than 2 to the power 3 minus 1, which is 2 to the power 2, which is 4. This is true. So you are getting that for n equals 1 and 2, it's not true. From 3 onwards, it's true. Let's check whether it is true for all n in n or not, because the option here is this is wrong, this is wrong, because for n equals 1 and 2, it's not true. This can be true. Till here we have obtained somehow for n equals 3 it is true, for n equals 4 it will also be true, but for every natural number it's true or not, we have to check that. We apply the very principle of mathematical induction. Let P of m be true. Let P of m be true, that is m factorial be greater than 2 to the power m minus 1. I have to show P m plus 1 is true. That means I have to show m plus 1 factorial is greater than 2 to the power m plus 1 minus 1, which is 2 to the power m. That's what I have to show. So what you do, you consider the left hand side, and don't forget this is your assumption, so you need to use this step in proving this step. Consider m plus 1 factorial. This is m plus 1 into m factorial. M factorial is greater than 2 to the power m minus 1. 2 to the power m minus 1 can be written as 2 to the power m upon 2. Like this. Obviously m is a natural number, m plus 1 upon 2 is a natural number. Not a natural number, but m plus 1 upon 2 is a positive number. 2 to the power m into this is clearly greater than 2 to the power m. Right? And therefore m plus 1 factorial is greater than 2 to the power m. That means Pm plus 1 is true, and therefore by induction, by first principle of mathematical induction, I can say that Pn is true for all n in n. So from 3 onwards it's true for every natural number. So it's true for all n strictly greater than 2 and for all natural numbers. Understood? Moving to the next question, we have Pn is given to be this. Okay. It is true for what all values of n. Again, if I try to talk about 1, for n equals 1, if we see, it is 2 into 1 minus 1, which is 1 equals 1 square, which is 1. So it is true for n equals 1, not a problem. In here, if I try to say, let it be true for n equals m, let Pm be true. Pm be true means this implies 1 plus 3 plus 5 plus and so on to m minus 1, this expression is equal to m square. I have to show Pm plus 1 is true. That means I have to show that when in place of m I put m plus 1, I get, in place of m you put m plus 1. So what you get, twice of m plus 1 minus 1, which is 2m, plus 2 minus 1, which is 2m plus 1. And before that, this term will be coming. This I have to show is equal to m plus 1 square. I have to show this. That is what is pm plus 1. Now, if I have to show this, consider the left hand side. If you consider the left hand side, you have 1 plus 3 plus 5 plus 2m minus 1, 2m plus 1. From 1 to 2m minus 1, I can use the induction hypothesis, which is that 1 plus 3 plus 5 plus 2m minus 1 is m square. So I can write this straight away as m square into 2m plus 1. Isn't it? What is this? This is plus actually over here. Right? Everything is with a plus sign. So when you replace m by m plus 1, you basically get 1 plus 3 plus 5 plus 2m minus 1 plus 2m plus 1. And this is equal to replace m by m plus 1 square, which is this expression. When you replace m by m plus 1, in place of m square, you get m plus 1 whole square. I need to show this left hand side is equal to this right hand side. This expression has been replaced by m square plus 2m plus 1. What is m square plus 2m plus 1? It is m plus 1 whole square, right? So your left hand side has come out to be equal to right hand side. That means the argument is not just true for n equals m, it is true for n equals m plus 1 as well, provided it is true for n equals m. And therefore, by very first principle of mathematical induction, from 1 onwards it's true. That means it's true for every natural number, true for all n in n. Clear? Next I have, it is saying that Pn is a statement such that if Pk implies Pk plus 1 is true, suppose Pk is true and it is implying that Pk plus 1 is true, then Pn is true for what? Now here if you understand, it is directly pointing towards the usage of first principle of mathematical induction. Just because Pk is true implies Pk plus 1 is true, I cannot say that it is true for every natural number, or it is true for n greater than 1, or it is true for n greater than 2. Minimum to minimum, I need one value at which I can calculate the truth or falsity of Pn. I need at least one value of n for that. Primarily, I need for n equals 1. Right? For n equals 1, if I am able to get the truth or falsity of my Pn statement, I can talk about then the n equals 2 stage and n equals 3 stage, n equals 4 stage. Right now I don't have Pn, so I cannot basically get the validity of the truth or falsity of the statement Pn for n equals 1 or n equals 2, whatever. And therefore I have no grounds on the basis of which I can say that just because Pk is true implies Pk plus 1 is true, therefore this is correct or this is correct or this is correct. And therefore the answer is that nothing can be said because the validity of this statement Pn being true for what all values of n starting from n equals 1 cannot be checked. Okay? Next question says what? Pn is 1 plus 3 plus 5 and so on, 2n minus 1 equals 3 plus n square. Which of the following is true? Is P1 true? Let's calculate for n equals 1. P1 is 2 into 1 minus 1, which is 2 minus 1, which is 1, equals 3 plus 1 square. It is saying 1 equals 4, which is clearly false. So no, P1 is not a true statement. Is it true that if you assume Pk is true, then Pk plus 1 will also be true? Let's do that. Let Pk be true. Pk be true means that 1 plus 3 plus 5 plus and so on 2k minus 1 is equal to 3 plus k square. This is holding. This is holding. I have to show when this is already holding, then Pk plus 1 is true. That means I have to show when I replace k by k plus 1 on the left hand side, what I get is this. Isn't it? You replace k by k plus 1, you get twice of k plus 1 minus 1, which is 2k plus 2 minus 1, which is 2k plus 1. Before plugging in k plus 1, you will plug in k, When you plug in k, you get 2k minus 1 before it. So this is the expression you get on the left hand side when you replace k by k plus 1. This expression should come out to be the exact same expression which is obtained when on the right hand side here you replace k by k plus 1, which is 3 plus k plus 1 square. I need to show this. Now when you consider this left hand side, just consider the left hand side, which is 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1. In that scenario, this much is already given as equal to 3 plus k square. So we can use that. We have to use the assumption to prove this, plus 2k plus 1. Now, k square plus 2k plus 1 is k plus 1 whole square, and therefore you have got that the left hand side is equal to 3 plus k plus 1 whole square. That means the argument is also true for k plus 1, and therefore if pk is true, this implies pk plus 1 is also true. Next, for all positive integral values of n, this is divisible by what? Okay, let's see. If I have Pn given to me for different values of n, I have to see. And till 1, 2, 3 stage, if I get a common number, I am going to take that solution. So here, Pn is given to be 3 to the power 3n minus 2n plus 1. n equals 1, you get 3 to the power 3 minus 2 plus 1, which is 27 minus 2 is 25, 25 plus 1 is 26, which is 2 into 13. For n equals 2, you get 3 to the power 6 minus 2 into 2 plus 1. This gives you 729 minus 4, which is 725, plus 1, which is 726, which can be written as 2 into what? 363, right? And therefore, when I am talking about again n equals 3, I basically get 3 to the power 9 minus 6 plus 1, which again can be written as 2 into something, you can check. And therefore, each time I am getting that for different values of n, my expression which is turning out in place of this is actually coming out to be written as 2 into something, 2 into something, 2 into something, which means all these numbers for every value of n are divisible by 2. This expression for every value of n is actually divisible by 2. Is it understood? So go through all these questions very nicely. That's it from my side. Thank you.